Class, let's go for it here. This is the end of the lecture. Actually, we can do a couple more things on Monday, just a little bit to finish off 4.5. But just want to clarify the issue that we had in class here, just so real quickly here. This is the second derivative test officially from the textbook here, page 400, and I had a senior moment. I'm so sorry here. And there was not a high school senior moment here either. That was a problem. Anyways, let's go for it here. So it says this on page 400. If it says that if the second derivative is greater than 0, then you have yourself a local min. If it is less than 0, you have yourself a local max. And then if it's equal to 0, then the question is it's inconclusive. You do have to test the endpoints here. So when we do this right here, the first derivative test, it's going down, it switches to going up, and then all along here, if the second derivative is always positive, which means it's always like this, all the way across, that means you have yourself a minimum right here. That's what that definition is saying on page 400 if you want to open to it. Then the other flip side is it's been going up, then it switches to going down, and if the second derivative, again from here all the way to here, from that inflection point on, if it was just always minus, then you got yourself a local maximum. Okay, that's the definitions there. We good? This is the piece. Now the question is this: if it's greater than 0, less than 0, and I should have added this into it here. So what happens if the second derivative is actually set equal to 0? What happens there? And it's inconclusive. That's the problem. Let me spell it correct. C-O-N, all right, inconclusive. Are we good? That's where we're at on that. So let's look at the problem that we had. This is exercise 3. We took the first derivative. Everything's fine. We declared that at x equals 0. We don't have a derivative. So we're looking at either a cusp, a corner, or it is derivatives at infinity. You got one of 3 choices there. All right, then we did the derivative, and we found out we have ourselves 2 answers for it. There's a +1 and a -1. Okay, so that's cool. Then we went to the second derivative here. So we found out the whole problem here again is x equals 0. All right, in this case, we just got x equals 1. All right, so now let's put it together here. So let's go to this little piece here. Let's start graphing this. So we got a 0, 0 marker right here. We have a -1, 2, 3, 4. -4 marker here. We have a +1 and a +4 marker here. That's what we have. Let's see what else. We're not looking at x-intercepts at this point here, at least for this exercise. So here's what we got. We got to connect dots together here, and so let's look at our derivatives at this point here. So we got the first derivative test, and yes, we're gonna build this out real quickly here because that's what I want to see. So we have 0, 0 as a critical point, -1 as a critical point, +1 as a critical point. So let's go back up to what we have over here. Here's our first derivative. And the question is, once you plug in test points, what's happening with the test points? Okay. So let's go for it here. And so what we want to do is we want to plug in something. Maybe a -5 would be good. Oh man, we're going to have to plug in a -1/2 into here. Maybe +1/2, and then maybe like +5. And so we'll see. And again, I don't care what the value is. I am only caring about the sign value here. And this is one of those you probably would just punch in the calculator in order to do the work here, as you are looking at the third root of -5. It's going to fly. So we have ourselves this little situation. We have ourselves a negative coming through. Then we have ourselves a positive here. have ourselves a positive still, and then a negative. So it looks like there is a decreasing to increasing change at -1. At 0, it's going up and then keeps on going up. So let's see how that's going to graph. And then at 1, there is a sign change from increasing to decreasing. Okay, so second derivative test. And so in this case, it only gives us 1. That was it. So according to the definition on page 400, because it was a 0 here, it's inconclusive. We have to sort of think about what's going to happen here on this. All right, that's our only critical point for the second derivative. And 0, that's right, it can't be 0. Okay, so we're looking at that right there. We're looking for a possible change in that behavior there. Okay, so let's go for it here. So if it's, let's do this here. If it's, let me give you the possibilities here. So this is a 0. So if it's a minus coming all the way through and a minus coming all the way through, we know that that should be a maximum. If it is a, let's say, minus here, then a plus, it's increasing, concave down increasing, and how would you even draw that? So it's concave down increasing, that's a nice one right there, and then it's decreasing but concave down, and it's a smooth curve, and that usually will not happen like that. Usually won't have those because that would be a corner at that point here. All right, so let's graph. Let's actually go back. The second derivative, this is the one we want. Plug into your calculator here, and let's plug in some values into that. Again, using your calculator. Most likely, unless you want to put in an 8. I guess 8 would work. 8 would work there. 8 would work there. Or -8 if you want to go from the left-hand side. If you want to do it by hand. Normally we do, let's just plug into a calculator. Let's see what the sign would be. Alright, and the sign turns out to be plus all the way through here, and then right at 0 it switches to a minus, and that's what we have right there. Okay, based upon all that, this is our contention right here. This is why I started the problem in the first place, that I have my senior moment right there. And so notice that there's no sign change. Yes, we have a critical point of 0, but there's no sign change of the second derivative. And so because there's no sign change, we have ourselves now back to this little definition. It's increasing, and then it starts decreasing, and it's concave down all the way through. Alright, so let's graph this here. So going down, concave up. So this one, going down, concave up. It would come down like this. And so here is concave up, and it switches to concave down, but there's still an increase. Alright, and then the other issue is it's undefined right there, right? We have first derivative and second derivative is undefined. So what's the only way that can happen, that we have a concavity change, but we just still have increasing, increasing, increasing? And so the only way we could do that is that we have a slope that went to infinity right here. So there's my infinity slope right there. They went up straight up for a split second, and then the concavity changed for us. And I could just draw that a little more curved there. Okay, and then we concave down, came down. And there should not be a corner here. It should be just a flat curve going off this way. About right there. And in order to make all sense of things here. And so we have, yep, we do have a minimum at -1, -4. We have a local maximum at 1, +4. And just a concavity, so this becomes an inflection point at 0. Alright, hopefully that helped, at least to bring things together here. Maybe a quick example. Let me just kind of show you another one here where it's going to do something similar. I'm just going to thought of this here. if you had something like this, like a fourth degree polynomial, again, just a quick, simple illustration. That's a fourth degree polynomial. If we were to take the derivative of it, it would be a power rule, so 4 goes in front, and then we have ourselves a 3 there. And then if you take the derivative of x minus 2, it'd still just be 1, so I don't even need to mention it here, but I want to see that second derivative again. That second derivative would be now 12, and it would be an x minus 2 to the second. So notice, if we were to solve this for 0, obviously we're going to have x is equal to 2 as an answer. This will be right, that's what we have here. It's a 0 for a second derivative. If I were to graph this function, this is a fourth degree power function here. It should just come down like this. It's going to come across like this, and it comes down steep, and then it goes back up. There's x to the fourth. And so there's a minimum right there. And so the first derivative test, if we were to set this guy equal to 0, in fact we should go like this. Divide by 4, still a 0. Cube root both sides, still 0, and x is equal to 2. So I have this one being a 0 as well. So the first derivative at 2 is equal to 0. I have all these 4 zeros. Then I have this one, and this one tells me that it crosses the x-axis at 2. Okay, so if we apply the first derivative test across here, and at here, there's my critical point at 2, and on this side, there should be a negative, right? Coming all the way down, there should be a positive that flows up. Okay, so then we're looking at that, and then we have a second derivative test. And again, we have a critical point at 2, but notice in this one here, if you were to go to the left side of it here, you would have positive, and you go to the right side of it, you go positive. So that there's no sign change for your second derivative, so therefore you know that this is a minimum. Okay, hopefully that explained the little piece that we were missing in class today.